Hey guys, welcome back to part 3. Today we're going to use CountVectorizer and TfidfVectorizer to create a vocabulary list and count the number of words. So let's go straight into it. We're going to first create something called a model. So we're going to call vectorizer equals CountVectorizer, instantiate it. So here, vectorizer is our model. Okay, and we're going to use the model to take in, so we're going to use the model to return a matrix, and we're going to call the matrix X, capital X. We're going to use a function called FitTransform, and then we're going to pass in the raw documents that we want to return. And just to give you an idea of what FitTransform does, FitTransform does two things mainly. One, it tokenizes. Okay, and number two, it counts. And what I mean by that is, let's take a string. For example, this is a string. Okay. And we're going to tokenize this, pretty much parsing by the white spaces and lowering it. So actually, this wouldn't be a good example. I want to, damn it, this Korean. This is a string. Okay. So we're going to do string dot lower and dot split. And this is pretty much the tokenization part. We're breaking it up, and then that didn't work. Well, why didn't that work? Because it's not returning anything. So if we do S, for example, then we're gonna have this. So it's breaking up, right? By this is a string. So we have strings like that. So that's the tokenization process. The count is counting literally how many times it occurred, the frequency. So we'll take a look at that. And the way we're gonna do that is we're gonna pass in lyrics here. One thing I did want to play with is the Forest Hills. I wanted to focus in. I wanted to narrow down on an album. So let's create a data frame called Forest Hills, and we'll use the label to sort of point it out. So we'll do df.album. Yeah, album equals 2014 Forest Hills Drive. I'm just going to see if that works. It didn't work because df is not defined. It's because I didn't run everything. So, okay. So that should work now. Cool. All right, we didn't pass anything here. That's why we're getting this error. So, just to look at what's here, we're gonna get this lyrics portion. Okay, so we're gonna pass in Forest Hills lyrics. So when we pass in that column, it's gonna create a list of lists of those lyrics. So when we do that, we have a matrix, and we can check out the matrix shape. And this means 13 rows, and this means 1,556 columns. And each column is a word. So we literally have a list of vocabularies here. And so we'll look at that. But before that, I want to add stop words, which is basically a list that you ignore the words that are in it. Sorry, let me say that again. So if you have filler words like and, as, the, stuff like that, it's going to get rid of it. And we're going to pass in English, because English, yeah, it's in this sklearn library, I think. Basically, it compares against the stop words list. So if we do that, then we're going to see this sort of go down to 1,366. Cool. Now, what does this mean, right? So let's look at it in readable format, because if we just do X, well, first of all, this gives a description of it. We get a sparse matrix, and a sparse matrix means a lot of the coefficients are zeros. So we'll look at that But if we do to array, right, we're converting it into an array. This is, this is a song, right? And the zeros are pretty much the occurrences of each word. But still, I mean, it's not really readable. So we're going to create a data frame, I think. Yeah, let's see. Yeah, we're going to create a data frame. So it's called Forest Hills data frame equals PD, that data frame. We're going to pass in the array to array. And for the index, just to make it clear that each row is a song, we're going to pass in Forest Hills from this data frame, right? We're going to pass in this column, title. And then for the columns, for the features, we want to pass in the get feature names. So from our model, right, this model will return the matrix, but this model is already trained on this, so it knows what words we've seen. So we're going to get columns vectorizer dot get feature names, and this is a method detailed in the documentation. So when we do that, boom, let's take a look at it. This is what I mean. This is the count and frequencies. So for example, wet dreams, right? These zeros means this is an aggregation of all the words that it's seen. So it hasn't seen any of those, hasn't seen years, yo, no yo in wet dreams. But there's one youngin. How do you see all the rows now? Well, okay, well, that's because of that option. This is weird, but let me just input an option here. PD dot set options display dot set max columns none. It's not right. Set option. There we go. So if we do that, then yeah, we can see everything. See, in wet dreams, he said the word ain't. So we probably got rid of the, ain't, and it shortened it to ain't. But basically, these are all the words. My eyes are getting dizzy from it. So, but this is why it's sparse. You see all those zeros, all right? So now, this is cool, but let's sort of make it more useful, right? Let's count up the number of words that he said the most in this album. So one thing we're going to do is we're going to use the matrix, sum it all up by column wise. So for example, this O2 part, we're going to add up everything in this column. So we'll get 1. And for each word, we get that. So for ain't, we're going to get a bigger word, right? But just to give you, an idea, let's look at love. Let's get the word love. See, in note to self, he said love 36 times. In wet dreams, he said it 9 times. I think that's the third row. Sorry, that's not. That's love yours. He said it 9 times. So yeah, we're going to count the number of words he said in this album. All right, so that's that. What we're going to do is first create a sum count. And this would be, I think this would be a list. Actually, no, it would be an array. So from here, this is our matrix, right? So we're going to use the matrix sum function, and this is numpy matrix function. And we're going to use the axis, set the axis to 0. And what that means is we're going to basically do this sum function on the column wise. So this is axis 0, this is axis 1, right? Axis 0 is by row, but because we want to sum for each column part, we're going to do that. If we do that, and we're going to get 1 row with the same number of features. So that's what we want, right? We want the sum for each word, right? And just, well, yeah, let's just leave it at that. First 1, as I talked about this column. So, That's good. And the reason why we're doing that is because now we have the number of frequencies for each variable, each feature. All right. Well, what's after that? Well, this is interesting actually. Vectorizer, the model, has a list of, or has a dictionary of all the words said. So, for example, if we do vectorizer our model dot vocabulary underscore, which is to say that it's like an inherent method attribute, you know, not, okay, I don't know how to articulate that, but it's like a secret method in a way. But anyway, we get our dictionary, right? And just to be clear, for each term, like verse, this isn't the number of times that it was said. This is the index for this. All right, so we have 1,366 columns. This is the index that's going to point to the word verse, and for everything else, vice versa. So if you want to get the index for love, for example, it show you that, oh, it's at index 700. Okay, so this is neat, and we're actually going to convert this vocabulary into, well, let's break it down so it's easier. Vocab list is that, okay? Actually, that's not accurate. It's dictionary. Let's get rid of that dot. All right, and the way why it's a dictionary is because if we do type vocab dict, it'll be a dictionary. Okay, cool, useful function, really. All right, so now we're gonna create something called a list of tuples. I think I'm saying it right. Tuples, tuples. I think I heard someone say tuples. Gosh, correct me if I'm wrong. But the reason why we're gonna get tuples is because we're gonna do vocab dict, and we're going to convert it into tuples, and we're going to do that via the items method. If we do that, we're going to get a list of tuples, as you can see by the parentheses. So that's a tuple, right? We have the word and we have the index. Cool. And just to confirm that it's a dict items object, you can just do that. Let's dict items. Okay. Now, cool. This is what I want. The list of tuples, which has the index and the sum count. Now, we're going to create a function to do this. And recently, I've been practicing list comprehension, recently being yesterday, actually. So let me just try this again. So we're going to create a master list, right? That's our list, right? Through the brackets. And what we're going to do is we're going to return, well, this is our expression. We're going to have word, and we're also going to have the number of times that word was said in this album. So we're going to use, and that's from here, right? So we're going to do sum count, right? And we're going to have these brackets, and why is because we want to point at this row, right? It says 1, but that's saying it has 1 row. The first row is 0, right? It's, yeah. And 136 is the number of items we have. So we're going to pass in something called an index, right? Just, you know, something to pass in. The reason why we're doing that is because now we have our expression. We're going to use, we're going to go through with our iterables. So for word and index in, and this is in the vocab dictionary, because in our vocab dictionary, actually, sorry, that's not that. So list of tuples, we have, if you remember, each tuple had the word and the index, right? So from that, we're getting the index and we're putting it into the sum count so we know what word we're looking for. And in return, we'll get a tuple with the word and the frequency. So if we do that, let me just double check. Yeah, but so that should work. But just to sort of not use list comprehension, what I'm doing is basically this. Index and tuples, temp tuple, word, and then index is coming from sum count 0 index, and then all we're doing is adding it pending the temp tuple. So this is the same thing, right? This function, well, not function, this, yeah, snippet is the same thing as that. We're going to the word index, boom. We're creating a tuple and then we're adding it, and then, yeah, so same thing actually. So if we look at our master list, boom, we have it. The verse was said 31 times, things said 13, peace 5, Uncle Phil, you know, rest in peace, Uncle Phil, said 1 time each. But, you know, why don't we sort of sort this, right? Okay, so we're going to sort this in place, right? And I learned this yesterday too, but it actually, I think it's finally clicking with me after seeing it for years. We're going to set the key, which is a parameter saying this is our sorting criteria, right? What's the sorting criteria? So we're going to use lambda x as x1. Now, just to explain what this is, lambda is an anonymous function, so it's being used to select this, the sorting criteria. Are we sorting by the word, or are we sorting by the count of each word, right? So x1 is pointing at 1 here, right? 0 would point at the word, so we're going to point at 1. And then we're going to do reverse equals true. And what that does is, so if by default reverse is set to false, so that means it's going to be in ascending order, right? You'll see 1 to, you know, 200 or something, but we're going to have it in descending, so we're going to have the highest first. So there we have it. We sorted it, and just to give you an idea what that looks like, this is the number of words that J. Cole said in Forest Hills Drive. Just to sort of look at only the top 10 words, we would use that. And as you can see here, you know, he said the N-word a lot, and, you know, love, you know, wanna, you know, and these can be filler words. They weren't detected by the stop words parameter, right? So actually we could create our own unique stop words list, right? So if we want to be like, you know what, get rid of every like, you know, then this would do that, right? We would pass in a list. But for now, we're gonna just set it to English. Gosh, why did I do that? No. Okay. So cool. We know the counts for each word. Well, that's good to know. Yeah. Well, that's cool. And CountVectorizer does a great job of doing that. I think that's really neat, right? Get an idea of what he says the most. Chorus, probably because we didn't clean that up. Probably we can do that. Fuck, he said 42 times. Anyway, now we're going to use the CountIDF library or class, because TfIDF looks at it a little bit differently. It looks, so this is the count of all the words from each song, right? From every song. Well, I mean, from the album. TfIDF is going to look at the importance of each word. So, for example, if love was set across all 13 songs, then it's going to regard it as not so important because it's been seeing it there. So, we're just going to take a look at that. It's same steps actually, but let's just trailblaze through this. Was it TfidfVectorizer? Yeah. That was stop words equals English. Then from, yeah, we're gonna create a model called TfidfVecTransform Forest Hills lyrics, and then from here we're gonna have the stop words. No, sum count. Y sum x is set to 0, right? And then we're gonna also create our that list of tuples. How should I do this? 1, okay, just to make it well, whatever. So from our model, we're gonna get I should know, our vector TF-IDF, like that vocabulary, underscore the items, then we'll get our list of that. Let's just go through this. So master list equals 1 equals, yeah, I gotta work on my names, but whatever. Should work fine. So from here, we're gonna do list word sum count. Actually, we already have that too. So it has 1 sum count 1 0 index, because we're gonna do forward index and list of tuples. Not a list. Yeah. Boom, boom, boom. Okay, and then we're gonna sort it right with key equals lambda. X equals x1, start 1, rest equals true. Okay. So we skipped looking at the entire array. Maybe I want to show that first. Yeah, I do want to show that actually. So we're gonna do that. So let's create a data frame called D, and we're gonna, create a data frame just to sort of compare with CountVectorizer. We're gonna send in the model to array. Index, you already know, it's Forest Hills title, and for columns we're gonna send in the vocabulary. So Y, no, that's not right. TF-IDF vect from our model, we're gonna get the vocabulary. That's not true. We're going to use feature names, right? Yeah. Is that wrong? Let's see. TGIDF is wrong. FIDF is right. Okay. So if we do that, you'll see that the numbers look different, right? We have floating numbers instead of integers. And so what these numbers represent are the importance across these documents. So the higher the number, the more significant it is in terms of the whole collection. Okay, I don't know if that's describing it accurately. So for example, M&M is 0.0. I don't know. I think a better way is to just show. So this is the difference, right? We're not counting the words. We're calculating the frequency, the importance of each word across the documents. Now, so I'm just going to get rid of this. I'm going to uncomment these. And when we show master list, let's do top 10. And this is the importance of each word, right? So before we had a count, set to 10. So the N word is 148 times said. 2 is saying that, yeah, it was that important. Dawn, don't, or don't, yeah. Wanna, for example, is 1. Love was 0.7, saying that it was important at times. So there we have it. Now we're looking at the importance of each word, right? So you could see a correlation with the number of words being said to deeming how important it was. Fair enough, but I don't think it's really accurate. So this is when we start tweaking the model, right? And this is where I think things get more interesting, because you want to fine tune it based on the Word documents you're working on. So the way I'm going to do that, or the way I have been doing that a little bit, is by, let's go back to our model here. TfIDF-Vectorizer, if you look at the documentation, has something called min-df and max-df. So max-df equals something and min-df equals something. This is something I'm still trying to grasp. But basically, max-df, if you set a number like 0.3, which actually I think is a good number for this, is going to do this. So while you're creating this model, ignore all the words that show up in above 30% of all documents. Okay, so let's just look at that so you know what I mean. So I set max df. This is a filter pretty much, right? Ignore all the words that show up in more than 30%. So basically it's going to ignore the more common words like no, man, because man probably showed up in all 13 songs, right? So what's 30% of 13? I don't know. But so it's going to sort of focus on that, right? So let's focus on the more words. Okay, whatever. So that didn't work. That's because the index is out of bound. Why? It's because we already calculated. I wonder if I did it too much. Oops. Oh, I wonder where that error is happening. From master list. No, shit. Shit, okay. I've been doing this wrong, actually. So this is why you gotta be careful with naming your variables. I've been using the list from above, which is inaccurate. So I'm gonna do this one more time. What? Okay. Nothing really changed because the words are the same. So all right, that makes sense. So we're gonna do max df 0.3. Let's see what changes, right? This is what we see right now. Now we're gonna ignore the words that show up in more than 30%. Hello, free, paid, air, beauty, believe, thought. Now these are less frequent across the documents, but they're deemed as important because of how many times they were said and across documents too, not just one. So this is interesting because I think we're getting closer to extracting the essence of this album, like the themes, if you will, like so this is where we continue to fine tune it. And MinDF, this is interesting. If we put in like 5, that's pretty much saying if ignore a word if it wasn't ignore a word if it occurred in less than 5 documents, right? So if you have the word, I don't know, beauty, and it's in 5 documents, if it's in less than 5 documents, then ignore it. I didn't wrap my head around the math here, but there's a relation between maxDF and minDF, so I can't do 5. 3 would work though, and it would change again because you're ignoring the words where it's happening in less than 3 documents. So then we have believe as being a very important word, happy, thought, maybe. So we could continuously play with this, right? Out of 4 here, right? Let's sort of increase the umbrella there, and then all of a sudden we see Hollywood being more important. So I think this is where you have to play with the model, right? Play with the parameters. But yeah, through this process, you can get a better idea of what the essence is of that album. But this is really small. We're only looking at 13 songs. So I'm curious what it'll look like if we look at the entire, album. And, actually we could do that. Let's see, I think we could just, okay, if we do df.lyrics, that should work. So I'm just gonna get rid of these parameters right now. Right, we'll keep the stop words list. All I did was change the data frame. Our main data frame, we're gonna look at all the songs, right? And I'm hoping that it's cleaned up enough. Yeah, because we did all the sorting from part 2. So that stays the same. Whew, okay, so the N word is now 14. Like is 11. I mean, it's pretty consistent the way I see it, right? Because of the count of words. Because if we change it for here too, where did I use it again? If we do that's getting a little messy here, but let's say I did from here too, right? For the CountVectorizer. Okay, vocab list is really big now. This didn't work because it doesn't match. I'm going to df that title. Right, we have 6,567 words now. Okay, cool. That's going to take more time to load. Not really interested in that though. I guess I can wait. Nah, I'm just going to get rid of it. Oh yeah, this is much bigger. Wow, much bigger. I mean, much. Is that right? Whatever. So let's see. Oh my gosh, he said the N-word over 1,000 times. All right, that's fine, right? But just to say, like, that's the correlation. Like, that's a lot of times. Yeah, he said 624 times. You know, it's important. But now this is where it gets interesting. Let's introduce the max DF again, right? And before, I think we saw a good result with 0.3, right? Ignore a word if it's been showing in over 30% of all songs. So let's do that. All right. And wow, okay, this is interesting. Hook, that's inaccurate because that could have been cleaned. LA, I wonder if he's referring to LA, like California, or it's law. I don't know. Yeah, okay, that could be a filter word that we could filter out. Oh, ma, I don't know. This could have some significance, right? Maybe he's talking about his mom. Night, mama. See, ma and mama, interesting. Hi, yo, free, interesting. Well, maybe it's not that interesting yet. We'll do MinDF set 5. Didn't really. Well, 5 isn't a lot actually. 0.5. Nope, that wouldn't work. So let's do 0.3. That wouldn't work either. Interesting. Anyway, I want to increase this. Well, first of all, I don't know, 50. That didn't work. You know what? For now, I'm just gonna get rid of that. Max DF 0.5. Get rid of field seen in over 50%. Yeah, so this is where I think you really got to understand your shit, because, you know, I think the relationship between MaxDF and MinDF can really alter what you're seeing. So you got to understand the data sets that you're playing with. But anyway, this is the end of this tutorial. Just wanted to show the number of counts of each word, and also just sort of look into how important each word might be in relation to, you know, how you parameterize your model. So yeah, guys, I hope this was useful, fun, entertaining, whatever. And let's see, I think this is going to be it for the data analysis on J. Cole series. I might do something again on his lyrics, but I'll just, you know, spin it off, create a standalone video, right? So thanks if you were watching from part 1, and I'll see you next time. Bye.